Uh, First is binary trees. We are going to study traversal of binary trees, height and depth, binary search tree and operations, and then graphs. Basically, introduction today. I mean, introduction of graphs, DFS, BFS, and all. So, without further ado, let's start. So, tree. What is tree? A tree is a nonlinear data structure made up of nodes connected by edges where data is organized in a hierarchical manner, that is parent child manner. Okay, so have all of have like use that folder structure in computer. So it's somewhat like that. There is always a root folder and subfolder. So the tree structure is somewhat like that. Now, so it organizes the data in a hierarchy instead of a straight line. So now let's move on to the whiteboard. Uh, so here I am going to talk about nonlinear data structure and linear data structure. Now, uh, suppose I have numbers 10, 20, 30, 40. Okay. And if I store them in an array, how are they going to be arranged? One after the another, right? So can can 10 directly be connected to 20 and 30 both in case of an array at the same time? No. So array and linked list is a linear data structure, but in case of tree, uh, a node can have multiple nodes. A node can be connected to multiple nodes. So a single node can be connected to multiple nodes. So this is where I cleared linear data structure concept. Okay. Now let's move to the PPT. Okay. So some terminologies. Uh, node is a basic element of the tree that stores data. Edge is the connection between two nodes. Root is the topmost node of the tree with no parent. First, listen carefully. I'm just reading, then I'm going to zoom into this picture and explain. Then, parent is a node that has one or more child nodes. Child node is a node that is directly below a parent node. Leaf node is a node having no children. Subtree is a tree formed by a particular node and all of the descendants of that node. Degree of a node is the number of children of a node. Okay, so let me zoom into this. Okay, yeah. So this is the root node. Okay, the topmost node having no parent node. Then this is the parent node, and these are the child nodes. Obviously, these are also the child node of root node. Okay, these are the leaf nodes having no children. These are also leaf nodes. Okay, so I hope this is clear till this. Okay, these are all basic. Now let me move. So next is binary tree. Okay, so what is a binary tree? It is a special type of tree in which each node has at most two children, called the left child and the right child. Okay, so uh, binary tree is going to have at most two children, either zero child or one child or two children. Can't be more than two. Okay, this is what binary tree is. Now, types of binary trees. This is also I'm going to give a reading and explain with the diagrams which I have in the next slide. So full binary tree is every node has either zero or two children. Okay, so I'll show you. See, it's a full binary tree. Either the node is having zero child or two children. Okay, so nothing much to explain. It's very obvious and clear. from the diagram. Okay. Now complete binary tree. Complete binary tree is all the levels are completely filled except possibly the last, which is filled from left to right. So complete binary tree is either all the levels maybe completely filled. Okay, that is like it may happen that all the levels are completely filled. Okay, or if not, then only the last level is incompletely filled, and that too it is filled from left to right. You can see here it is filled from left to right. Like it's not here. The nodes are not here, and it's not that this is empty. Okay, so this is what is I mean by complete binary tree. Now next is perfect binary tree. All internal nodes have two children, and all leaf nodes are at the same level. Okay, so perfect binary tree. See, all the leaf nodes must be at the same level. Okay, if this won't have been there, 7 and 14, then 5 would have been a leaf node, and 3 and 6 would have been a leaf node, would have been the leaf nodes. So then it won't be a perfect binary tree, because in that case, the leaf nodes would be at different levels. Okay, so I hope it is clear. Then next is balanced binary tree. The height difference between the left and right subtrees of every node is at most 1. That is less than equal to 1. So height difference of the left subtree or right subtree of every node should be less than equal to 1, right? So this is what is balanced. This is what we mean by balanced binary tree. So you can see here the height of the left subtree is 3, and the height of the right subtree is also 3. The difference is less than 1. Okay, so this is what we mean by balanced binary tree, and it should be valid for every node. If you see, for every node it is valid, the height of left and right subtree difference in height is less than equal to 1. Okay, then I guess degenerate. Yes, degenerate or skewed tree. That is, every parent node has only one child. Okay, uh, this is, see, you can understand that only every parent is having only one child. So it's uh like here it is right skewed. You may have left skewed also. Okay, but only one child it will have. So this is degenerate or skewed binary tree. These are some of the types of binary trees you should keep in mind. Okay, now let's move ahead. Okay, now some important properties of binary trees. Each node has at most two children. I have already told you this, either 0 or 1 or two children. Next is the maximum nodes at level n. Okay, so you can see this. This is 0th level, first level, second level, third level. So it's very obvious. You from here only you can derive what's happening. You can see first level is having one node, second level is having, like, each parent node is having two children, right? So each node so next level is having 2 to the power 1, that is two nodes, right? Then the level 2 will have four nodes. So 2 to the power 2, 4 nodes. So this is what is 2 to the power L. That is, if Lth level is there, then 2 to the power L nodes will be present at that particular level, maximum nodes. Okay, if the level is obviously filled. The maximum nodes in a tree of height h. Okay, so height of the tree. Suppose height of the tree. This height of the tree is 3. Okay, now count how many nodes are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you can see 15 nodes are there. right? So like it's obvious. First level is having one node, okay, plus second level is having two, third level is having four, fourth level is having eight. It's always like that up to 2 to the power h. From there the formula comes 2 to the power h plus 1 minus 1. So this is what is maximum nodes in a tree of height h. Okay, so next is minimum nodes for height h. Yes. So minimum nodes can always be possible in a skewed tree, skewed binary tree, because only because the parent is having only one child in skewed tree. So minimum node will always be. So if I take this example, uh, height uh, height is 3. So how many nodes will be present? You can see, right? If height is 3, 4 nodes are present. Okay. So this is h plus 1 uh, is the minimum nodes for height h. Now minimum height for n nodes. Okay, so n nodes are there. Now see, maximum like maximum nodes that can be present for height h is to the power h plus 1 minus 1, right? So this minimum like n nodes is less than equal to the power h plus 1. You can see this is very easy actually, right? So from here this h comes log base 2 n plus 1 minus 1. Okay, so I hope it is clear. Now number of edges, if n nodes are there, then n minus 1 edges will be definitely there. Any small tree you take, you will understand. It's very easy thing. Okay, so let's move ahead with our discussion. So now let's come to traversals. Okay, now first is in order traversal. In case of in order traversal, uh, in means the root will be in between. Okay, so this is how I remember, like left, root and right. This is how we are going to traverse the tree. Okay, first the left node, then the root, then the right node. Okay, this is algorithm that traverse left, then uh, visit root, and then traverse right. Okay, so let me move to the whiteboard so you can see. If I write in order traversal for this, how I'm going to write. First is left, so I will move to the extreme left. Okay, so this is the extreme left. We don't have any left subtree. Like there is no left subtree of this. So 4 will be there definitely. Then what is the root of 4? 2. So 2 comes. Then uh, left root right. What is the right subtree of the root? 5. Then 5 comes. Okay. Then what is the root of this 2? Like 1 is the root. Like we are done with the left subtree of this root, right? Now left subtree is done. After left subtree, what do? We print the root. So here we print the root. Okay, then we move to the right. We move to the further left. Okay, further left. This is leftmost of this subtree. So then we left is printed again 6. Okay, then we again 6 is root is 3. So 3. Then again the right 7. So we are done with the left, root and right. Okay, so I hope it is clear how I'm writing the in order. Now next is the code. Let's come to the code part. There's a recursive approach I have used. This is the base case that if root is null, then we return. Okay. And first we call the roots left, then we see out the root value of the root, because first we traverse left, then visit the root, then traverse right. So we print the root, then we traverse, keep on traversing right. Okay, this is the uh, code. So I'll explain you here. This is the root. We're not bothered. We move left of root. Okay, that is f of 2. Okay, now again f of 4. Again it will call the left of 4. Left of 4 is null. So whenever we get null, we return. So we return, and we return an f of 4. After f of 4, we print 4. Print the root value. So 4 is printed. Then we move to the uh, right of 4, which is null. We return. So we are done with this. F of 4 gets over. We return. Okay. F of 2, right? F of 2. So we are done with the left part of f of 2. We print 2. We print 2, and then we come to the right part. Right part. Then again same thing. F of 5. Then f of 5 is the root. Then we move to the left. Null. Return. Print 5. Print the root. Then again to the right side we move. It's null. We return. So we are done with this call. We return. We are done with f of 2. This entire part is over. Return. This is again f of 1 is there. So we print the root. This root we return back, and this we print 1. Okay, we print 1. Then again we move to 1's right. Again we move to f of 1 is over. Then we move to 1's right. I mean, this f of 1's left half is over. Then we print 1. We move to the right. Then again we move to the right of this, and further we move to f of like this. We f of 3. Then f of 3's left we move to. Okay, then again f of 6. Then f of 6 is left. When we move, we find null. Then again same thing. We print 6. Again null. Return. So after this we return to f of 3. We print 3. Then again f of 3's right part we call. And again same thing, null on both the sides, and this gets printed. Then return. This comes to end. So I hope it is clear in order. The time complexity is big of n is all the nodes that we are visiting. Okay, and space complexity is big of h. Like h is the height, like it's the recursive stack space. Other than, of course, we are taking big of n to store this, but other than this, at a first go maximum we are traversing the entire height of the tree. So that is the recursive stack space. Okay, so now let's move on to the pre-order traversal. That is root, left and right. Okay, so first pre-order means first root comes, then left, then right. Then this is algorithm, same thing actually. So let me tell. So root, same base case. First we'll print the root value. Okay, then we go on to the right. Then we go on to the then we go on to the left. Then we go on to the right. Okay, so let me explain here. Reorder. So first is we'll print the root value. So this is the root. One is the root. We print it. We move to the left of one. Again, uh, f of two. F of two. Two is the node root node. Print it. Move to the left of two. Left child of two. Okay. Then f of four. Print it. Move to the left. Null. Return. Then again move to the right. Null. Return. So we are done with this. Then again we return here. Okay. So here we move to uh, right part of 2. Okay, right part of 2. uh, I mean root, f of 2 is the root, then root's right part. Then again same thing. If it is null, like for like yes, of course, f of 5, first 5 gets printed, first root value will get printed. Then this side, left, it will move. Null, so return. Right, null, return. Then it returns back. Okay, it's done. Now again return back to 1. Okay, and move to the right half of 1. This is the root. Move to the right half. F of 3. So f of 3, immediately print the node, root node, and move to the left of root. F of 6. F of 6, print it. 6. Similarly, you go this side, right, left side null, right side null, return. Then again you go to the uh, right half of 3. Then you find f of 7. F of 7, 7 you print it, and this side null, return, this side null, return, 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 ends. Okay, so the time and space complexity remains the same, because there was just a slight change of the algorithm, not major change. Okay, then post order traversal. Post order traversal, let me move on to the post order traversal. First left, then right, then root. Post means after, so root will be after. Okay, so this is the code that the base case remains same. Then your first we move to the left, 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 as you can see. Then you move to the right, 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 and then you print the root value. So I'll show it to you here. Okay, so this is the root. Move to the left. Move to the left. Okay, so left, left. Now move to the left. You see null is there. Then again you move to the right. You see null. Then you print the 4. Okay, return, you print the 4. Done. Then uh, the left call is over. Now right call. Okay, right of 2. So 5. So again left, right, null, so return. Okay, this is over. F of 5, print it, return. F of 2's left and right both are done. Print 2. Print the root. Return. For node 1, we are done with this half. Now move on to this part. Okay, so now move on to this part. So move to the left. Left. This is the leftmost node. Then left again. So null, return. Right again. Null, return. This is done. 6, print it. return. Then again to the right half you come, then again same thing, you print 7. Okay, again return. Done with this half, print 3, return. For 1, done with the left half and right half, print 1. Okay, so is it clear? I hope it's fully clear. Okay, now next is level order traversal. Okay, level order traversal, what it does is it will print level wise. Okay, like first it will print, like it will store 1, then it will basically return a vector of vectors. So first it will look like this 1, then in the next level you see you have 2 3, so it will have 2 3 here. Then the next level, what all you have, 4 5 6 7, so it will have all of them here. This is what is level order traversal. So let me show you the algorithm. Initially, if root is null, we return an empty answer, vector. Then we use a queue here. So we create a queue, and initially we will push the root node in the queue. Now, while the queue is not empty, we will like store the current queue size, and using a for loop, we will traverse the entire queue. Okay, and like we'll store the queue dot front. Okay, uh, and pop the front node and add its value to the current level. Okay, and also if it is having a like left node, then left child, then push it to the queue. If it is having a right child, push it to the queue. In the same way, like if queue size is 2, like first you pop the front, then you again like process with the like another, like then you process with another element. So you throughout the size of the queue, you are going to process, and after the for loop you are going to push the levels into the answers. Okay, so I will show you. It's just a vague idea I gave to show you how it's working with this tree only. So initially I'll push the root node. Okay, then uh, if the queue, like queue, the queue is having 1. Okay, then the size of the queue is, you understand that is 1. So we pop the front node 1, we pop it, and we store it in the level vector. Okay, and if that node which we pop is having a left child 2, you push it in the queue. If it is having a right child, that is 3, you push it. The queue is having 2 3. Okay, now next step, also at the same time, every time after the for loop ends, you're going to push this level vector into the answer. So that is, I'm not explaining. Okay, the next is again, currently 2 is the size, if you see, right? So first we will pop 2. Okay, see, we are going to pop 2. So we popped out 2 and we added this to the level. Okay, we popped out 2 and we added this to the level, and at the same time we push the children of 2, that is 4 and 5. Then we popped out 3 and we added to the level. We popped out 3 and we added to the level, and we pushed the children of 3, that is 6 and 7. Okay, so you can see that it is, the level is having this 2 3, which is 2 3. Got it? We push it in the answer. Then again in the next, it is like very obvious that throughout the queue is having this, right? So first you'll pop 4. 4 is having no child node. So we add to the level. Then you pop 5, add 6, add 7, add. So the level is having this 4, 5, 6, 7. So is it clear? I hope it is clear. The entire dry run. Okay. So time complexity will again be big of n because all the nodes we are processing. And space complexity, if you see, it's somewhere the width of the tree, you can see maximum width. There's a levels you are storing. Okay. Maximum width, and for binary tree, it's nearly n by 2. Okay. So I hope it is clear. Now, next is height or depth of a binary tree. Okay. Now, depth of a node means for a node, I'm telling that from the root to the node, the path is the depth of a node. And height of a node is from the node to the deepest leaf. Okay. And when it comes to the like height of the tree, then tree is represented by its root. So root to the deepest leaf. Okay. And depth of the tree, which represents the maximum depth of any node. Okay. Depth of the tree, that is the root to the deepest node, and deepest node is in turn the leaf node. Okay. So height of the tree and depth of the tree somewhat becomes the same of the tree, I'm telling. Okay. Okay. So let me explain you uh, height of the tree. So here height of the tree is a number of nodes, maximum number of nodes from the root to the leaf node. Okay. So here it is 3. The height of the tree is 3. Okay. So first let me show you the see the code. If the root is not uh, like if the root is null, then return 0. Okay. And we are what we are actually doing is we are uh, traversing the left half, then the right half, and we are returning 1 plus max of left and right. Okay. So 1 for itself, the node itself, and the maximum number of nodes on the left and maximum number of nodes on it's having on the right. Okay. So initially this is the root. Now like we traverse to the left. The left is having like left, then again we move to the left, right, then again left. So left of 4 is 0, I mean null, so return 0. This is returning 0, right is also returning 0. Okay, right of this node is also returning 0. So entire this will return, what it will return is 1 plus 0, right? So it will return 1. Okay. Now right of this part we will see now. Okay. So right, now left of this again 0, right of this again it will return 0, and 1 for itself plus 0, that is left, max of left and right is 1. So it's going to return 1. Okay. So for this node, this left half and right half is returning 1. So we need to take max of left and right, that is 1 plus 1 for this node, this particular node. So 2. So this is going to return 2. Now we move to the right of 1. Okay. Then again we move to the left, and the left works in the same way. Left will return 1, left will return 1, right it's not having, so it will return 0. So maximum value that it's going to have is 1 plus 1, that is 2. Okay, so this right subtree is going to return 2, left subtree is going to return 2, and 1 plus max of 2 is 2, so 3. So I hope it is clear. Okay, now let me move on to the next, that is the diameter of a binary tree. So what is diameter? Diameter is defined as the total number of nodes on the longest path between two end nodes. Okay, so this is what we mean by diameter. Let me move to the whiteboard. Okay, so actually what diameter is, it's the longest path in the tree. So intuition is, at every node, the longest path passing through that node is simply the height of the left subtree plus the height of the right subtree. Okay, so here we are recursively uh, computing the heights and updating the maximum diameter along the way. Okay, so like if the node if it like if node is null, root is null, then return 0. Okay, left's height we are calculating. Height I have already explained to you in the previous question. Okay, right's half right half's height we are calculating. We are calculating keeping track of the maximum diameter, that is left plus right. We're keeping track of the maximum diameter, and we are returning 1 plus max of left comma right, that this is the height that it is returning. Okay, so like if for each node we are having the height of the left and right subtree, then we can easily calculate the diameter, that is the sum of height of left and right subtree, right? So this is what is the thing. I'm going to do the dry run. So this is the node, root node. We move to the left. Then this node is having 1, returning 1 as the height. I've already previously told you same thing. Only this line becomes an extra thing. So this returns 1. Okay, so left is having 1. Okay, now we move to the right. Right is also returning 1. So right is having 1. Now diameter left and right of this node is having 1, 1. So diameter will have 1 plus 1, that is left plus right 2. Okay, 2. And at the same time, what this 2 are going to return to this is height 2, right? This was having height 2. 1 plus 1. I have already previously explained. Okay, fine. Now move, it will move to this. Now to the right half. Okay, left half, leftmost node, this is its height is 1, it's returning 1. If it is returning, then again to the right we move, this is also returning 1. Okay, so again 1 plus 1 2. So if the max, like if somewhat the diameter would have been 3, then it would have stored 3, because we are computing, keeping on track of the max diameter, right? And at the same time, this node's height is 2, so it is going to return 2. This is also going to return 2. Actually, it's returning height, right? It's returning the height. So uh, in this case, here also the left and right, like the left subtree's height and right subtree's height is 2 and 2. The diameter is 4. So max is being stored, so diameter value becomes 4 ultimately. So I hope it is clear. This question can also be solved in an alternate approach using double BFS. Like you can use a BFS from any node to find the farthest node, and apply another BFS from the farthest node, uh, and find keep on calculating the max distance, which will give the diameter. So in the later half of the lecture, BFS and DFS will be taught. So after that, you can try on your own. So the next part is BST, and it will be continued by Ayush.
Am I audible, guys? Yes, I am. Then let's continue the class. So now we are going to learn about the BSTs and BST, binary search tree. A binary search tree is a binary tree where every node, all values in the left subtree are smaller than the node, and all values in the right subtree are greater than the node. And both left and right subtree are also BSTs. Like in this example, you can see like 8 is there as a root node. Now 3 is smaller than 8, that's why it is in the left side. And 10 is a greater than 8, that's why it is in the right side. So let's take an example and try to create a binary search tree. So let's say, sorry, let's say I have example 8, 3, 10, 6, 1, 14, 4. So let's try to wait a minute. Why it's not visible? Wait a minute, guys. I have to connect my screen to the laptop first. Yeah. So this is an example, and we used to create a binary search tree while pushing this element one by one. So because there is no element, then 8 will be your root node, and if you'll again push 3, if you'll again push 3, then because 3 is smaller than 8, it will come to the left side. And now for 10, because 10 is greater than 8, that's why it came to the right side of the 8. And then for 6 is smaller than 3, 6 is smaller than 8, and greater than 3. So 6 is first of all smaller than 8, then you will come to here, and then it is greater than 3. That's why it is came to the right side of the 3. Now for 1, it is less than of 8, and it is also smaller than 3. That's why it is came to the you know to the left side of the 3. And for 14, 14 is greater than 8 and greater than 10 also, so it will come to the right side of 10. And for 4, 4 4 is less than 8, 4 is less than 3, 4 is greater than 1, so it will be here, it will here. So this is how you can create uh, a binary search tree one by one by pushing all elements into the into the tree. So let's understand how you can insert a node into the tree. So for insertion, what were you were doing when I was explaining you this, what you were doing, like there is a node, like there is a 12. Now you have to push this 12 in this binary search tree. Then how you can do this? So first of all, you will check it by the root node, whether it is smaller or greater. So 12 is greater, so you will uh, come to the right side, and you will now check with this element. So now 12 is greater than 10 also, so now you will come to the this element. Now 12 is less than 14, so you will you will add this element 12 here. Okay, so what you are doing, if wait a minute, if root val is less than key, then is less than key is less than key, then you will go to the right subtree, then you will go to the right subtree. Okay, and else you will go to the uh, left subtree. And at this point, when at at this point, you will also check if root is equals to null. Then you will directly add these elements to the you know to add this element to at whatever whichever position you have to, like because this node will be represented as this. Here you will add the value, here we will add the reference of the right pointer, right subtree, and here you will be add the reference of left pointer. So the left will be what, 0. So you will when you will go to the left, you will the root address will be what, null. So you will just add the new node, whatever I will call this, I will call this as new node. And you will just directly add the you will just directly call this function and add the value by passing the key value here. So I'm just giving you the overview of the function, and now I'm just going to show you the code so that you can understand the implementation of insertion in binary search tree. So you can see that here you are checking first that if root is equals to null, then you will do what, you will just add the new node with the value key. But if it is not, then you will check if key is less than root data, then you will go to the you will call the you will call the insertion function again. It's the recursive approach. You will call the recursion function again with passing the root left, because you are going to the left direction. Okay, and you will pass the same key value, and whatever would be this, you will just store it in the root left. Okay, and then if it is not, If it is not, then you will consider it as what, key greater than root data. Okay, if key is greater than root data, then you will do what, you will whatever, then you will go to the right direction. Then in right, you will call another function insertion. You will call another, the same function again with the point, with the reference root right and key. So in this way, you can just create the, you can add an element into the, into a subtree, into a binary search tree. Okay, and this is your algorithm. That's what you are doing in this, you know in this insertion function. And the time complexity, the worst case complexity would be big of log n for this approach. Okay, now we will see searching. Now, for searching, first of all, you are searching. So for searching, you will need a key that you are searching in the tree. Like here, this is your binary search tree. This is your binary search tree, and let's say you have to find out 6, that whether 6 is present in the uh, bst or not. So what you will do, because you know that what value you are finding, then in whatever way you have just created that bst, in the same way you can find out. Okay, in the same way you can find out, like if this 6 is less than 8, if this 6 would be less than 8, then you will search in the left subtree, and you will come to here. Again you will you will check whether 6 is less than 3 or greater than 3. So 6 is greater than 3, so you will come to this point. And and when you will find out that the 6 is present, at that point of time you will return from there, and you will just return this node, return this, the reference of this node. Okay, so this is the way. So for searching, what you are doing, for searching, what you are doing, if again root well, but let me check that. There I have used data. Okay, so I'm using the data. Okay, so root data. Okay, if root data is less than key, then you will check in the search in the right subtree. Okay, and while searching, you will do what, you will call the recursive function, or call the same function again. Okay, same call the same function again. Else, if root data is greater than key, then what, then you will do, you will search in the left subtree, and you will do again the same thing that you have done here. And else, else what is remained, like root data is greater than less, is less than key, greater than key, then here root data when equals to key, when equals to key, then you will, you get what, you get what, you got the key that if this number, this value exists. So you will just return, you will just return, like if it is bool function, you can return yes, or if it is not, then you can do just return the, return the address of this, so we can return the root directly. Okay, so this is the way for searching. Like you can see here, uh, what we are doing here, that's in, when we are searching uh, with the value key, we'll check if root is equals to null, or root data is equals to key, then we'll return root. Okay, and if it is, if key is less than root data, then we'll search in the left side of the subtree. And if it is not, then we have only remained one option, then we can directly return this, and with the same function again. and we'll I mean we directly call the same function again with the right side pointer. So by this way you can search in a BST, and there I have given you the algorithm of it. And let's talk about the time complexity. If the best case time complexity would be what? Best case time complexity, like if root equals to what, whatever you are searching, like if you are searching 8 and you got it here, then what? Then the the time complexity would be what? Big of 1. You in a single pass you get whatever you wanted to. So the best case time complexity would be what? Best case time complexity would be big of 1. And in the worst case time complexity, in the worst case time complexity, in every time what you are doing, you are, while you are checking, you are just dividing the elements. Like you are first, like if you are searching 6, you got your answer in the third pass. Like in the first pass you will be here, in the second pass you will be here, in the third pass you got your answer. Okay, so every time you are just you are just like in binary search, you used to half half your the range, and that's what we are doing also here. Okay, so the time complexity for this also will be, in the worst case it will be big of log of n. And for best case, sorry, let me check this. Sorry, this is your average case. The average case complexity would be big of log of n, and the worst case complexity will be big of n. When it will be big of n, like you have right skewed right skewed BST, or left skewed BST. What is right skewed? When your tree looks like this: 8, 10, 12, 14, 16, 18. So let's say you are searching for 18. So what you will do, you will just first you will be here, and then you will check, you will be here, and then you will come here, and then you will be here, and then you will be here, and then yeah, you got your answer. So the, because here total, so how many passes you have done total n passes. You have whatever would be the number of the nodes, that number of passes you will have to do. So the time complexity this will be what? The big O of n in the worst case scenario. And this is your right skew. And if your tree looks like 8, 6, 4, 2, this is your left skew. It's leaning towards left direction, and that's why it's left skewed, and it's leaning towards the right direction. That's why it's the right skewed subtree. Okay, now talk about the deletion. Okay, so for deletion, like you can check, like if you have to delete this element, then you don't have any childrens for 4. Okay, because it doesn't contain any childrens, you can directly delete this element by passing the right pointer to this element as a null. By passing the right pointer to this element as a null. Okay, you can directly do that. Let's say now if you have to delete this, and this is your case 1, when when it contains no children, or the leaf node, when it is the leaf node. But if it is uh, a node and it has one children, then what you will do? Then whatever would be the one children, you will just whatever would be the your one children, you will pass this here. You will remove this, and you, whatever would be the reference of it, you will just uh, you will just I mean, you will just replace it here, like 1 is replaced by 4, and you won't see 1. Okay. And what I'm saying is, like, if I can draw it here, or let me erase something. Like, if you have one children, then 8, 3, 10, and you have to delete this, then you will just, whatever would be the 4, you will pass the reference of it to the left pointer of 3. So you're in this way, 4 will be here, and then 6 will be here, and 14 will be here, and then 12 will be here. So in this way you can do this. In this way you can do this for, if it contains one children. But what if it contains two children? Okay, what if it contains two children? Like in this case, three has, like, for if you have to delete three, if we have to delete three, and it contains two children, 4 and 6, then what you will do? You will find out the in order of this tree. You will find out the in order of this tree. So what will be the in order of this tree? I will just write it down here. 8, 3, and so this was the tree. Okay. uh 6. This is your 6. This is not 16, this is 6. So what you will do, what you will do for deleting this element, you have to delete this. So first of all, the uh, you will find out the in order of this tree. The in order of this tree. So in order is what? A left, root, and right. So the in order traversal would be, uh, wait a minute guys, I have to share my screen again. Sorry for that. And in order traversal would be what? First you will come to 8, and you just now, understand how to, uh, find out the in order. So I'm just writing it down. Okay. So it will be, so first you will come to 8, and then you will go to the left, and then you will go to the left, and then there isn't any left, then you will just print this, and then again you will go to the right, there isn't any right, so you will again come back to 3, and you will print 3, and then go to the 6, there isn't any left, there isn't any left, there is, then you will print 6, there isn't any right, then you will just return back to here, and then you will print 8, and then you will come back here, in the right direction of 8, then you will see there isn't any left, so you will print 10, and then you will, you will go to the right, and then you will see there is 12, so you will write 12, and then 14. So this will be your in order traversal, in order traversal. So you have to delete what? 3. You in order to delete 3, what you will do? You have to replace this element as, as a in order, in order predecessor, or in order successor. So what is in order predecessor? Predecessor is this element, because you have to, if you have to delete this, you can replace this element as your predecessor or the successor. This is your successor, and this is your uh, predecessor. I don't know about the spelling, but this is your predecessor and this is your successor. Okay. So why we are doing this? To not having any ambiguity. Like, yeah, it has two children. It has two children, and whenever you will have two children in the real life, also, when you will have more than one children, then you know that, there would be some ambiguity of properties on all of these things. So because it has two children, what you can do, you can follow a process, this process where you will get, you know your successor. I'm explaining you it via successor. So this will be your successor, and you will just replace it with the with this element. So you will just replace it with this element, so if you replace it, then it will become 6. It will become 6. And when it will become 6, now what is your task now? Initially you were deleting 3, but now you will be deleting what, 6. And now you will see that, it has no children. So it directly converts to the it directly converts into the first case of when you were deleting the leaf node, and how you were deleting the leaf node, you will just directly remove that node. Okay, so you will directly remove that node. So what you will get for here: 8, 6, 4, 10, 14, and 12. So this is your what, remaining BST after deleting the node 3. And you can see it that this is your BST also. So this is how you can, delete a node from the BST. And this is your, case 1. This is your algorithm. Case 1, when it is leaf node, delete directly. When it is one child, replace node with its child. And when it is case 3, when it will have two children, replace with in order successor. you know I have written successor. You can also do it by the predecessor. And when you will use the predecessor, delete that node. uh, okay. And for this, the time complexity would be equals to what, big O of log of n. In the worst case, big O of n. That's what, I have explained it here. uh, and when it will be worst case in big O of n, and when it will be your big O of log of n. And I haven't given you the code. Okay, so you can find out the code, or if you'll say that, I will just add it when I will be sharing this PPT to all of you. Okay, so I will add this, I will add the code in this PPT, because the code was pretty large, so I didn't add it. So now let's start the graph portion. Graph. A graph is a non-linear data structure consisting of a set of vertices, nodes, and edges connecting those vertices. So graph is a function of what? A vertex and edge. V represents set of vertices, E represents set of edges. Okay. E represents the connections between the nodes. So for example, you can see A is connected to B, and A is connected to C. You can see it here. Okay, A is connected to B and A is connected to C, and B is also connected to C, and B is also connected to D. There in the graphs you can have, uh, in the graph you can have cycles also. Like, what I mean by cycle, like, like A, B, C. So this is what your cycle is. You can, your cycle. This is just a cycle. Okay. So, uh, and what were your vertices? A, B, C, D is your vertices, and edges is what? A, B, A to B. There is a connection. There is a connection between A to C. There is a connection between B and B to C, and there is a connection between B to D. Okay. So these are what? These are your edges. This represents your edges. Okay. Now, vertex, node, a point in the graph. These are all your, the what I can say, uh, a words that represent something like edge. A vertex is your node. Like A is your what? A is your node. C is your what? Node. B is your what? Node. And A to C represents a connection, and that connection is your what? Your edge. Connection between two vertices is your edge. Degree is like, a vertices is connected to how many vertices. Like if A is there and it is connected to B, C, D, E, then, the degree of A would be 4. Degree of A would be equals to what? 4. Degree of A would be equals to what? 4. And path क्या होता है? Sequence of vertices connected by edges. Sequence of vertices connected by edges. Like you can see, like this is your one of your path. Okay, this is your one of your path. So these are all what? These are all path. Okay, and a tree is also a graph. Okay, a tree is also a graph, but tree doesn't contain any cycles. Okay, where graph can. And cycle, I just explained it, a path that starts and ends at the same vertex. That will be your uh, cycle. And graph terminology, uh, you all know that, I know that, but let me finish it in a hurry. Like undirected graph means what? No edge direction. You can also come to A to B and B to C. Okay, there is no direction. Directed graph, like like if A to B, there is a direction. There is a direction. Like you can go to A to B, but you cannot go to B to A. So this is your directed graph. This is what your directed graph. And A to B, there isn't any direction. There isn't any direction. So you can go to A to B and also from B to A. So this is your undirected graph. And weighted graph, like when you will be going A to B, I have given you like while there is a meaning. Weighted graph presents you some meaning to the when you will move to A to B, the cost will be equals to what? 10 rupees. And for when you will move from B to C, the cost will be equals to what? uh, Cost will be equals to what? 12 rupees. So 12 rupees. So this is what? This is your the weight. You have represented every edges as some cost. Okay, you can also represent it as some weight, like whatever. The unweighted graph, the no weight. Connected graphs, every vertex reachable, like all of the vertex are reachable. You can also have some, you can also have multiple portion of components of graph, like A to B, B to C, C to D. Okay, and this is your one component, and another component is your F to G, G to H, H to F. So this is your another component, and these all are graphs. So there can be many component. So but these are what? These are not connected. So these are what? Disconnected graph. These are what? Disconnected graph. And connected graph is what? There would be only one component. Cyclic graph, when a graph contains a cycle. Acyclic graph, when there is no cycle. And complete graph क्या होता है? Every pair of vertices connected. Every pair of vertices connected. Okay, tree connected होनी चाहिए. Tree would be what? First of all, it would be connected, and it won't contain any cycles. Bipartite graph, vertices divided into two sets. Okay, like bipartite graph is what? This is your two sets. Like there is some vertices A B C, and there is some vertices E F G. Okay, this all are connected to, in somehow. Okay, these in a group itself, it cannot contain to each other, but like A cannot contain to B. This is wrong. Okay, F cannot contain F cannot have an edge to G. Like okay, so F cannot go to G, A cannot go to B, A cannot go to C. This is not your bipartite graph. Okay, you can only go to from this set to this set. Okay, so this is what your bipartite graph is. And then directed acyclic graph, DAG graph, directed graph without cycles. Okay, like you can understand it by the meaning. Okay, sparse graph, few edge, dense graph, many edges. That's it. Okay. So now we are going to understand the representation of a graph. How you can you can represent a graph. Like, let me explain it with an example. Okay. So let's say you have a graph. You have a graph 1, 2, 3, 5, and then it is not directed. Okay, it is not directed. It's my habit, just causing some errors. So 3, and then you can go to 8, and then you can go to here. Okay. So how you can represent? So for representation, you will have two kind of you know uh, you can say data structure or whatever. So the first one would be what? Adjacency list, and the second would be what? Adjacency matrix. Sorry for the spelling. Okay, let's talk about the adjacency list. Adjacency list. What is adjacency list? So whenever there is a connection between 1 to 2, what you will do? Uh, you will first of all create the adjacency list of all of the nodes. Like, how many nodes do you have? Uh, Sorry, 3. Let's call it as 4, and then it is 5. Is what your 5. So 1 to 2, and 1 is also connected to 5. Okay, and there isn't any more connections. Okay, so you can go to 1 to 2, and you can also go to 1 to 5. And for 2, you can go to 1, you can go to 3, and you can go to 4. And for 3, you can go to 3, you can go from 3, you can go to 5. From 3, you can go to you can go to 4. You can go to you can go to 4, you can go to 2, and you can go to 5. Okay. And for 4, you can go to 2, and you can go to 3. And for 5, you can go to 1, and you can go to 3. So this is what your adjacency list. Whenever there is a node, like 1 to 2 is a node, so you will, for 1, you will add whichever node it is connected to. Like, if 1 is connected to 2 and 5, so you will just add it here. And for 2, the same 1, 3, 4. And for 3, the same 1, 4 to 5. And for 4, this is also. So this is your you know adjacency list. And this is what your adjacency list. Okay, you can see here, 1 to 2, one is connected to 2 and 3, so it is 2 and 3. And for 2, it is connected to 1. For 3, it is connected to 1 and 4. And for 4, it is connected to 3. And how you can create this? You can initialize it like this, vector int adj, whatever name you prefer, and whatever the number of vertices would be there, just add it 1. Because we used to prefer that a node every node is represent you start representing from 1, not from 0. If it is 0, then let's keep it as v. If it is not, then add 1 at least. For int I equal to 0, I less than e, how many number of edges is there, and I plus plus. And you can just take the uv is your what? The connection. Okay, like u to v, there is a connection. So for undirected graph, adju adju, this is your, this is when you write adju, when you write adj, you directly come to here at this point. Okay, like your 3. Now this is your what? A vector. This contain a vector. So like, if u is 3, and u is 3, and your v is what? V is 5. V is 5, then you will just do it is a there is a connection between 3 and 5 and 5 and 3 because it is undirected. So it is a U which is here and push back 5. So in this way you can just do it, and if it is directed then keep it like that, and if it is undirected then repeat it, and repeat this one more time and pass it here V and here U. So in this way you can get that, get your adjacency list for your undirected graph. And for adjacency matrix, like whichever node is here, like this, we have a graph 1 2 3 4, and we represent it as this, uh, the row as 1 2 3 4 and the column is 1 2 3 4. If there is a connection between 1 to 2, then you will represent it as uh, 1, and if it is there isn't any connection, then you will just keep it as it is. Okay, so you will just mark it as 0. So for this, there is a connection between 1 to 2, so you will go to 1 comma 2 and you will just mark it as 1, like we have did here. And for 1 to 3 you can check 1 comma 3 is also 1. For 2 comma 1 this is also 1. For 3 comma 1 there is also 1. For 3 comma 4 there is also 1, and 4 comma 3 there is also 1. So because it is undirected, we are checking the both ways. Okay, and in this way, you can create your adjacency matrix. um, you know it's nothing, you just create a matrix, and if there is a connection, then go to that, you know that u comma v or v comma u, and place it as one. So now let's talk about the BFS first. BFS is your breadth first search. So in this, first of all, read the statement. Breadth first search is a graph traversal algorithm that visits all neighboring vertices first before moving to the next level. It follows level order traversal and uses a queue. Okay, so in BFS, first we visit the node. Okay, and then we used to explore all the all the adjacent nodes, Okay, and then we used to repeat this process. We used to repeat this process, and then you will be able to get the, the BFS. So for BFS for BFS, we use queue a data structure, okay, and a visited array. Why visited array? Because, like, you go to 1 to 2, so 1 to 2, okay, this is undirected. So for this, if you create a adjacency list, then it will be 1 to 2 and 2 to 1. Okay, and, like, if you go to 1 to 2 and you didn't mark that 1 is already visited, then when you will be at 2, you will again go to 1, and then 1 you will again come here, and then you again come to 2, and then this process will happen. This process will never stop. It will go till infinity. So, in this way, you will not be able to get anything from here. So you have to mark it as visited. Like, whenever you create a visited array, 1 2, okay, when you will be at 1, you mark it as visited. Now you go to 2, and when you will reach 2, you will mark this as visited. Okay, you will mark this as visited, and now you will be when you will be at 2, you will come here, and then you will check whether this is visited or not. First it will check this is visited or not. If it is visited, it won't go to this, one again. Whether Rather, it will check whether there are other nodes are here, which are unexplored. Like if there it contains 5 and 6, then there also 5 and 6 will be there. So one will we will not go to one again because it is explored. Okay, it is explored, so we directly go to 5, and we again and we will just repeat this process uh, uh, to get whatever we wanted to. Okay, so we use q uh, we use q to you know what next element we want to explore. Like when you will be at one, you explore two. Okay, because there is only one adjacent element. But how you will be able to know that you have to explore two again? For two, if you will not explore two again, you won't be able to get five and six. So for this, if we keep the track of the all of the adjacent elements, and we used to whichever would be the first element in the queue, we'll just try it, and to explore it again in the same way, and we'll just repeat this process to get the get the BFS traversal. And if we will have if I have to give you an the example, then I can think of like one, two, three, and three, one, two, three, six, 8. Okay, so if you'll start from here, this is not undirected, first of all, and this is your starting node. It represents your starting node. Okay, if you'll start from here, then first of all, will this is your visited node. This is your 4 and this is your 5. Visited, 1, 2, 3, 4, 5, and this is your queue. And queue works on first in first out principle. So uh, well, first, because it's a starting node, we'll just push it here. Okay, and we'll just pop out this value, and we'll check. We'll just pop out this value, and we'll check whether what are those adjacent element that are connected to 2, that are adjacent to 1. So there are what there are first of all, 1 is visited. Now 2 and 3 are adjacent, so we just add the 2 and 3 in here, and we marked it visited. Okay, because we have visited those nodes, and we have marked it here. And then because in the next element in the queue is 2, we just pop out this element. And when we'll pop out this element, we got 2. That's what I was talking about. Okay, and now for 2, we will have what we will have adjacent node as 1 and 3, but 1 and 3 are already visited. You can see here, this 1 and 3 are already here, so we can't revisit again. So we just return it from here, and we again go to the 3. We again go to the 3, and we'll just pop out this value, and we again check whether there is more element that are whether there are adjacent element that are unexplored. So yes, there is some unexplored element connected to 3, which is 4, and 5. So we will add it into the queue. We will add it into the queue and mark it as visited. Okay, so when we will be at the 4, we'll see there isn't any we have 3, but 3 is already visited, so we'll just return it. Okay, and then we'll go to 5, and we'll see that 5 is already visited, so we just marked it as it is. So in this way, that this traversal works. Now I'm going to show you the code. Like, if you can see, or I can increase the size. Okay, so BFS, you have seen the starting node. You can see, you can take anyone. Okay, and this is your adjacency list, and this is your number of vertices. And you have here, you have created a visited array with with all of the values as false, and there you have created a queue. And you have when the started node is there. So because we are starting from some node, we have visited that node. Okay, visited that node, first of all we have to visit that node, and then we have to explore that node. Okay, so because it is visited, we marked it as true, and we again just pushed it into the stack, sorry, queue. Okay, and until queue becomes empty, we'll just repeat this process, and this in this process will pop out the front value, will pop out the front value. Okay, and we are doing it here, and we'll print that, and whatever would be the neighbor of that, that node, whatever would be the neighbor of that node, for that neighbor will check whether it is, if this is visited, if this is visited, then continue, then don't visit that node again. Okay, don't visit that node again, and if it is not, then mark it as visited and pushed it into the into the queue. And in this way you can have your, you know bfs traversal. Okay, and this is your this is your algorithm, like mark source as visited, push source into queue, while queue is not empty, pop front node visited, push all unvisited neighbors into the queue. And that's what we have did. Okay, if it is okay, I'm going to explain it to you, the dfs. And this is your dfs. And with while coming directly to the dfs, I'm just, first of all, I'm just want you to give you the brief idea of dfs. Okay, so the dfs is depth first search. Depth first search. dfs is your depth first search. So whatever, whichever path we will take, we'll go into deeper. Okay, we'll go deeper into it until we get any leaf nodes, like uh, a, b, c, d. Okay, and e, uh, k, whatever. Okay, so this is your, uh, this is your one of the graph. Okay, you can say, you can say that, it is a tree, but I've told you initially when I was continuing the class, that tree is also a graph. So I'm just explaining it to you here because you can understand it in a better way. So when we'll be starting to a, we'll just check what are those, what are those, what are those adjacent element. You will say, yes, we have b and k, we have b and k. So I'm saying that take b first, take b first, then you won't care about k. Okay, if you will choose to come to b, then you won't visit, if you will if you will come to b, then you will at that point of time, you don't care about the k. Okay, you will just leave it, and when you will come here, you you will just repeat this process. Okay, you don't care about the k, will will do that, but not now. Okay, not now. And then we again see that, for this b we have two, you know child nodes, c and d, and we can choose anyone. Let's take this one. Okay, let's take this one. So we have again chose this one. Now what we are doing it here, we are not exploring all of the adjacent values. No, we are just not exploring all of the visited value, and then rather we are going deeper into it. Whichever node we are choosing, we are going deeper into it. Like, we first go into this b, and then we go into this until we get the leaf node. So we got the leaf node, and so we got the leaf node, and from there you will return. From there you will return, and you will check there, there uh, is there any other unvisited nodes. So the b will say yes, there is some unvisited node, like c is there. So you will again go to c. Now, like a, b and d was there, and now you are visiting c. So the traversal would be look like a, b, d, and now you are visiting c. Now you are visiting c. So you will add it, c here, and now you will say again that, is there any node. So yes, there is only one node. So you will go to e again. Then when you will be here, you cut the leaf node, you will return. It will say again that there is any remain, there is any unvisited nodes is there. So it will say no, there is not any unvisited node. for C there isn't any there is not any unvisited node, so it will just return it from here, and then it will return it from here, and you will just go to the K and you will just write it. So this is your DFS traversal. This is your DFS traversal. And in this DFS traversal, first you will visit this A, and then B, and then D, and then C, and then E, and then K. So this is the way that you can get your DFS traversal. And for tree, this is your what? This is your uh, I think it's your pre-order. It's your pre-order traversal. For tree, it is your pre-order traversal. DFS is your pre-order traversal, and BFS is your level order traversal. Okay. So in the DFS we use stack. And in the DFS we use stack and visited. Like here also we need something like why we used to visit the visited node again. Why we used to do that? We don't do that. We don't do that. Okay, first of all, for that, for keeping the track of all of the visited nodes, we use the visited array, and then we will use the stack. And if you will be using iterative approach, okay, like you will be if you will be using iterative approach, like you want to perform all of these things using for loop or while loop, whatever. Okay, so explicitly you will have to initialize the stack. Explicitly you will have to initialize the stack first. But when I was teaching you recursion, I told you that for keeping the track of the state, you internally the recursion use the stack. Okay, for like in which instance you are there. Okay, and then it moves on to the next instance and the next instance. Okay, and then it will start backtracking while taking the popping out to the top element of the stack. So this is the way, where if you'll be using recursion, for implementing DFS, you don't need to initialize the stack. Okay, you don't really need to initialize the stack. You just directly run your code, visit, mark it as visited, and that's all. So I'm just showing to you the code, like void DFS and node, whichever node you are starting. Okay, and then vector int adj, your adjacency node, and your visited node. Okay, visited array first of all. And whichever node you wanted to start, you will mark it as visited. And what you will do, you will just print it. Whatever node you will want to whatever node you have visited, you just print it. And then whatever neighbor would be there, in this way you are getting all of the neighbors to that node. And in the first, when you get any unvisited neighbor, you go in we go into it. Okay, and then you will repeat this process, and because it is unvisited, you go into that node and call this DFS function again. Okay, and it will go again and run this function, repeat this function again and again you got the until you got what, then leaf node. Okay, so for this, time complexity would be big of v plus c, and the space complexity would be equals to big of v. And this is your algorithm. Mark current node as visited, visit the current node. If you would have visited, again repeat this process. Don't care about the other adjacent node, and go into deeper into it, and traverse every unvisited neighbor recursively. Backtrack when no unvisited neighbors remains. Repeat until all vertices are visited. So these are the process. And if you will be writing iterative code, you will it's pretty a large code. It's pretty large, but yeah, when you will be using DFS by recursive approach, it's a simple and it's a very small code. So that's it for the today class, guys. And if you have any doubts, you can ask. And let's end this class, okay, now. So thank you, guys.